Hello, everyone. In the previous video, we talked about the first type of improper integrals, and that's when you have an infinite limit of integration. So you can think of that as being unbounded in the horizontal direction. Now, what we're going to talk about in this video is the second type of improper integral, which is when you have a vertical asymptote for your function. And you can think of that as having a function that is unbounded in a vertical direction. So the process of handling these types of integrals, as you're going to see, is actually quite similar. We have to treat them as a limit. The difference now is that your limit is not going to be, say, x going to infinity. It's going to be x approaching the asymptote from the left or right. So let me start by illustrating with an example. So imagine you're given the function 1 over the square root of x. So y is equal to 1 over root x. So if I sketch this out, we know that this thing has a vertical asymptote at y equal to 0. That's your singularity, because you have, when you put x equal to 0 in there, you get 1 over 0. And so here's my picture. And I have y equal to 1 over the square root of x. And maybe I ask you to compute, or I say calculate, the integral from 0 to 1 of dx over the square root of x. So that is the area under the curve between 0 and 1. So let's say this is 1 right here. Then what we can do is we can do something similar. Because this is unbounded as we approach 0 from the right-hand side, we are going to fix some lower limit that is not 0 and compute the area between, say, a and 1. And then we can let a go to 0 from the right in our computation. So let's start with finding the area between a and 1. So we have a all the way up to 1 of dx over the square root of x. Now, if you want to, you can write this as a to 1 of x to the minus 1/2 dx. And now you just need to add 1 to the exponent, divide by the new exponent. In this case, you get 2 times the square root of x, going from a to 1. And now plugging in the bounds gives you 2, that's the upper bound, 2 times the square root of 1, minus 2 times the square root of a. And you can do the same process as what we did for these infinite limits. You can now say that you can ask yourself, what is the limit here? So the limit is a goes to 0 from the right of this integral. So this area is slowly moving to the left and it's approaching. And now that we've computed this integral, we see that this is just taking, the limit is a goes to 0 from the right of 2 minus the square root of 2, 2 minus 2 times the square root of a, sorry, which is clearly equal to 2. So therefore, we would say that this integral is equal to 2 in much the same way that we handled the first type of improper integrals. Okay, so let me give you a general prescription for handling these things. Let's put it under a definition. And this definition says integrals of functions, that become infinite at a point within the interval of integration are, now we'll put this in red for emphasis, these are improper integrals of type 2. And just like the type 1 integrals, we have 3 different ways to handle these things. So let me list them off. So the first one says that if f of x is continuous on, say, the interval AB, sorry, let's make this closed or open, AB, and discontinuous at A, at x equal to A, then the integral from A to B of f of x dx is equal to the limit as, say, C approaches A from the right of C to B f of x dx. So just like what we did with the 1 over the square root of x. Now, obviously, we have the second case where you have discontinuity at the other end. So if f of x is continuous on A inclusively and B exclusively, and discontinuous at x equal to C, x equal to B, then the integral from A to B of f of x dx is now the limit as C approaches B from the left of A to C f of x dx. Okay, so that handles the 2 cases where you have discontinuity at one of the end points. There is one more case, and that's when you have discontinuity inside of the interval. So let me write this one down for us. So if f of x is discontinuous at x equal to C, where A is less than C, which is less than B, and continuous everywhere else. So continuous on the interval A to C, and so the union C to B. So basically continue everywhere else in the interval. Then the integral from A to B of f of x dx has to be broken up into the areas where this thing is continuous. So you get A to C f of x dx plus C to B f of x dx. Now, if you have multiple points of discontinuity inside one interval, you would just do the same thing. You break it up onto each one of the intervals where you are continuous. And of course, in cases where the intervals are finite, then we say that it converges. So we're using the same language from the previous improper integrals. And if the interval is infinite, then we say it diverges. Okay, so we've done one example here with 1 over the square root of x. Let's take a look at another one. So an example. So does the integral from 0 to 1 of dx over 1 minus x converge? Okay, so we can see immediately that this function has a singularity, a vertical asymptote at x equal to 1. So that puts us firmly in the realm of case 2, because the right endpoint of x equal to 1 is a point of discontinuity. And so that tells us that this integral 0 to 1 dx over 1 minus x should actually be thought of as taking the limit as b approaches 1 from the left of the integral from 0 to b dx over 1 minus x, which is the same as the limit as b goes to 1 from the left of, now we can take the antiderivative of this thing. You might want to do a substitution. It's entirely up to you. I'm going to just jump through it. This is the negative logarithm of the absolute value of 1 minus x. And this is running from, maybe I should put square brackets around it so it looks nice, 0 to b. So this gives me the limit as b goes to 1 from the left of negative logarithm of 1 minus b. Now, the reason I can drop my absolute values here is because b is smaller than 1, which makes 1 minus b positive. Okay, so we can pay attention to that small detail here. If you didn't do it, that's okay. You can still keep the absolute value around it. And then when x is equal to 0, you get the natural logarithm of 1, which is equal to 0. But now what happens? As b goes to 1, you get ln of 0. And we know that ln has a vertical asymptote. You approach minus infinity as you approach 0 from the right. And the minus infinity becomes plus infinity because you have a negative multiplying this logarithm. So this thing is equal to infinity, sorry. And so therefore, this integral diverges. So the area underneath the curve here is infinite. There is no finite area below this thing. Okay, so you can see that the process is almost the same as the type 1 integrals. It's just moving to the limits. It's very, very similar. We are probably, by now, we're probably very good at finding antiderivatives. And so like I emphasized in the previous video, really you're just sort of taking one more step by adding in the limits. So let's do one more example here to finish this off. So let's evaluate the integral from 0 to 3 of dx over x minus 1 to the 2/3. Okay, so the first thing that I can see about this is that there's a vertical asymptote at x equal to 1. So if I put x equal to 1 in there, I get 1 over 0, which is infinity. So that means if I scroll back for a moment, sorry, actually right here, I'm in case 3 because the function is a rational function. It is continuous everywhere that it is defined. So it only has one problem point, and that is at the vertical asymptote. So what number 3 tells me to do is to break up the integrals. So this tells me that the integral from 0 to 3 of dx over x minus 1 to the 2/3 is equal to the integral from 0 to 1, so up to the problem point, and then from the problem point to the end. Okay, so then maybe we'll call these integrals, maybe this is integral 1 and this is integral 2. We'll solve integral 1 first. Now, integral 1 is from 0 to 1 of d of x, of 1 over x minus 1 to the 2/3. Again, this is the right endpoint, so we're in case 2. So we set up a limit. The limit as b approaches 1 from the left. The integral from 0 to b. I'm going to write this a little nicer. Again, if you'd like to, you can do a substitution here. I'm going to go ahead with this. And so I get the limit as b goes to 1 from the left of, and in this case, you get 3x minus 1 to the 1/3 running from 0 to b. Sorry, that 0 looks like an a maybe. And so in this case, what you get is the limit as b goes to 1 from the left of, now let's put all this in, 3b minus 1 to the 1/3 plus 3. And in this case, if you just plug b equal to 1 into this thing, the whole first term disappears and I get the nice finite value of 3. So then we can do the same thing. And to evaluate the second half of this interval, so this was the integral from 1 to 3 of this piece right here. Again, the problem point is on the bottom of the interval, the beginning. So we're going to say this is the limit as a goes to 1 from the right now of the integral from a to 3. Let's put it like this again, just so it's easier to work with. We've actually already computed the antiderivative here. So in this case, we can set this up very similarly, and we get 3x minus 1 to the 1/3 running from a to 3, which gives me following. So it's not going to clean up very well. I'm actually going to get 3 times 2 to the 1/3. So I don't know what that number is. It doesn't have a nice, it doesn't simplify nicely, so I'm going to leave it. And then, minus 3x minus 1 to the 1/3. Sorry, that should be a minus 1 now. And allowing 1 to go to 0 in this thing is going to cause this component to disappear on the end. And so I'm left with 3 times 2 to the 1/3. Maybe I'll put that in a bracket. So actually, you know what I'll do? I'll write it like this so that it's distinguished. And so therefore, putting the whole thing together, the integral from 0 to 3 of 1 over x minus 1 to the 2/3 power is equal to 3 plus 3 root 2, which this thing doesn't really get any prettier. There's not even really a point to factoring out the 3, but nonetheless, it's there. Okay, so this has been fairly straightforward. I think it's sort of handled in the same way as the infinite integrals are handled. You just have to turn things into a limit. And the nice thing is, most of the time, if you forget to do it, things are still probably going to work out the way you wanted them to. You sometimes have to be careful when that vertical asymptote is in the middle of the interval. If the vertical asymptote's on one of the endpoints 9 times out of 10, 99 times out of 100, whatever it happens to be, you're probably going to be fine without looking at the limit.